Hi everyone, my name is Trojan, and today I'm going to be discussing the solution to the problem team, which is given by 401C. So it's a 1400 rated problem with the tags constructive algorithms and 3D. So let's quickly look at the question and what it wants us to do. So going over this really quickly, we have two friends and they have some deck of cards which contain the numbers 1 and 0. So these guys are superstitious and they believe in laying down these cards in a very specific pattern. And if they don't do this pattern well, or if they're not able to do this pattern, they are unlucky. So they have certain criteria for this pattern. So the first criteria for this pattern is there wouldn't be any side adjacent cards with zeros in a row, which essentially means if I were to go it over here, if I were to say, so you can't have any number of zeros in a row. So you'll need to have something in between them, or you'll just need to have one zero. So you can't have these adjacent zeros in a row. And secondly, there wouldn't be a group of three consecutive cards containing the number one. So uh, their second condition being you can't have three ones together. So what this would look like is you can't have three ones together. So 1 1 1 is false. So you can have either 1 1 or you can have two ones or you can have one, which is valid. Let's say that's given by V. So going back to the first condition, this directly implies that if you have a certain number of zeros in like the in so if you have a certain number of zero cards, you'll have to have some ones in between them to not make these cards adjacent to each other. That's what they want to imply, but we get that realization much smoother in like the example they've given us. So let's head over there. But before that, how are they giving us the input? So we get n cards with zeros and m cards with ones, and we're given that as an input, and n and m can get to pretty large numbers. Um, so if there is a valid sequence, we need to print this valid sequence of zeros and ones. If there is no such sequence, we print a -1, saying, boss, we can't do that. That pattern is not possible with the number of cards you've given me. So let's look at an example here, 1 and 2, where 1 is n and 2 is m. So if I were to write that down, 1, 2, and m 0, 0, 1. So for the answer, I would say this could be 1, 1, 0, since, or 0, 1, 1, or 1, 0, 1. Because the criteria we have, two ones can be together, which is true. And zero, we don't need to really worry about the zeros being together because there's only one zero. And basically, these three are the combinations that are valid, and all these three are valid for this particular example. So let's quickly delete this. Um, and if we were to look at another example, 4 and 8. So we see that we have two ones and then 1 0, two ones and 1 0, two ones and 1 0, followed by 1 0 1. So here we can see the zeros are not adjacent to each other, they're filled by ones. And there also exists a case where there's two ones in between, and sometimes there's one in between. So this is something to be essentially observed keenly, because this is essentially part of our solution and what comprises of our solution in the first place. Also, if we had to look at the one of the criteria where this fails, so if we look at 1 5, so fairly simple, we have 1 0 and 5 ones. If we stack that 0 anywhere, we'll need to put the 5 ones together, and this clearly fails that 3 ones can't be together. So this pattern can't be found, so we just say -1. Can't do this, boss. It's not fair to whoever is doing this. So let's So essentially, what we need to do is before we can even check if this pattern or how this pattern exists, we need to check if this pattern can exist in the first place, right? So how do we check if this pattern is valid or based on the number of cards they've given us? Let's go back to the criteria that they've given us. The first one being zeros can't be adjacent together, and at max you can have two ones together, or you can have one together. You can't have three ones together. So if we take this example, so let's say we have a few zeros together. So let's say, like, yeah, let's say I have three zeros together. If I have these three zeros together, for my criteria not to break, I need to have one over here and another one over here. So this essentially ensures that the zeros are not adjacent and our first criteria does not break. Quickly, if we look at another example for, let's say, five zeros, we can see that we need four ones, which is exactly one less than the number of zeros that we have. So if we see the obvious pattern here, let's say m is the number of ones and n is the number of zeros. So we essentially need n to be greater than n minus 1. That is the valid thing that we should have to ensure that these zeros are not sticking. So this is the minimum criteria, right? M can be bigger than this. But that also is a maximum criteria, because if the number of ones is too much, like the example they gave us over here, we'll find that they end up going overboard and there are three adjacent ones together. So there needs to be some kind of maximum criteria to ensure this doesn't happen. So let's go back to this example, right? Let's say, let's get rid of this. Let's say, since the criteria they've given us, there could be two ones sticking together. Let's say we have two ones sticking together here. So we can see obviously that we have twice the number of ones now, considering that we can have at most two ones together. So if initially it was n minus 1 ones that are required, now we can say that, look boss, I need 2 times n minus 1. Correct? But we also need to consider the fact that we're in the second rule. We're not just thinking of the first rule. So we're no longer constrained by just keeping the zeros, not adjacent to each other. So we can also have ones outside of this. Where else can we have ones? We can't really have one down the lane here or something like that, right? You can have ones over here, or you can have ones over here. Again, going back to the rule they gave us, we can have a maximum of two ones, right? So that means we'll have two ones over here at max and two ones over here at max, which means you'll have 2 plus 2, 4, correct? So this gives us our upper criteria, which tells us, look, boss, this is the maximum number of ones you can have. Beyond this, you'll have ones cascading or repeating together, forming groups of three, which is against our rule that is given to us. So if we were to simplify this, that would look like 2n minus 2 plus 4, which would turn to be 2 times n plus 1, because you get 2n plus 2. If you take the 2 outside, you get 2n plus 1. So if this is the lower criteria, and just write L for lower. If this is the lower criteria, I can safely say this is the upper criteria. So we need to make sure that the value of n stays between this upper and lower criteria. So before I even check whether a pattern can exist, I need to check whether these conditions are true. Then only, otherwise it's just a waste of computation, right? I don't need to check whether this is possible or not. So once I check that both of these statements are valid, I can go ahead and check for the pattern. So how do I do that? Since this is like a complex statement, I would say for a simple if condition, also since we're checking for the inverse of these statements, as in we're checking if either M violates this, as in M should be, if M should be greater than n minus 1 and M should be less than 2n plus 1 is the condition we need. But since we're looking for the negative of that outcome, or when M is actually less than n minus 1 or M is greater than 2n plus 1, we'll essentially be flipping these signs. So what that could look like is you'll have M, one second, yeah, you'll have M less than n minus 1 or M greater than 2 times of n plus 1. So this essentially is telling us that if any of this is true, if M is less than n minus 1 or if M is greater than 2n plus 1, we can go ahead and print minus 1, which indicates that it's invalid and which indicates this pattern can't be found. So this is our first criteria to understand whether this can be even formed, whether this pattern can be even formed. Once we've understood whether this pattern can be formed, now it's up to uh, us to figure out how this pattern is formed, right? So we need to essentially, since we're kind of following a greedy approach, we can go ahead and uh, use this in our scenario where we have multiple cases based on the values of m and n, which is based on the values of 0 and 1. So if you were to write that in, if I were to skip deriving that, and if I were to tell you how that would look like, and then tell you how I arrived at those, that would lead you to four conditions, where two are major conditions and two are minor conditions, where you'll have, let's say, use a different color. So you'll have case one, which is denoted by C1. You'll have m greater than n. Case two, you'll have m is equal to n. Case three, you'll have n greater than m. Sorry, n greater than m. And case four, you'll have n is equal to 0. And for this, you'll have n greater than m, and yeah. So let's look at these conditions and what these mean in the first place, right? So let's take a example input for us to better understand what it essentially is. So let's look at 4 and 8. 4 and 8. So once we find out that this is true, we'll go ahead and look at the number of zeros and the number of ones. Only when we have adequate number of zeros and ones will we go ahead, and our first priority would be getting these zeros to not stick together. So we'll have a singular one and a singular zero to ensure that this doesn't happen, right? But if, let's say, we have an excess of ones, which is what we're seeing here, is m greater than n, we can go ahead and essentially use that to our advantage, and we can print two ones together and one zero together. Uh, so if this pattern were to repeat, so it'll look something like this. So we have two ones zero together and one zero together, two ones together and one zero together, which is kind of what we get everywhere, two ones together and one zero together. So what this does is essentially we can burn off these extra ones that we have while still using the zeros and while still maintaining the criteria that they've given us. But let's take an example where m is equal to n, or this is 4 and this is 4 too. So that means we have an equal number of zeros and 1. So our priority needs to be, I'll just move this a little bit. Yeah, never mind. All right. So let's say we have an equal number of zeros and ones. That would mean we'll need to have 1 0 with 1 1, 1 0 with 1 1, and 1 0 with 1 1, 1 0 with 1 1, so that the zero rule does not uh, does not ruin our pattern, and we still burn out these ones. So as you can see, this is a valid answer because zeros are separated and you have 1 at max together. So that doesn't really break either of our criteria. But let's say, so you can majorly solve any sort of m and n values using these two conditions, but you'll eventually get to a place where you'll either have extra zeros or extra ones, which is where we'll need these micro conditions, conditions 3 and 4, where we'll check for n greater than m or n is equal to 0. So first, let's look at n greater than m, right? When do we get this? N greater than m, as in the number of zeros is greater than m. We get this only to be true when m is equal to n minus 1. Essentially, we have one more one. Essentially, so this would be, let's say, yeah, my bad. I think it's the other way. So let's say you have 4, so this will be 3. Yeah. So if I were to take that example, first I would check if m is greater than n, which is not true. M is equal to n, which is also not true. N greater than m. So I'll go ahead and print uh, the I'll go ahead and print whichever is greater. So I can print a 0, which is in excess here. So I'll print a 0, which gives me so I'm obviously gonna keep track of these m's and n's, or the number of zeros and ones. I'll be explaining that later. But if I were to really get rid of this example really quickly, so that would look like 3 and 3. Since m and n are equal, I can print the rest of my pattern, which looks like 1 0 1 0 1 0. So you have 1 2 3 3 ones and 1 2 3 fours. So that's what the pattern would look like. And if I had the condition where n is equal to 0, or the number of zeros is 0, that just means we have an extra 1. So we'll go ahead and print this one. So since we have these conditions locked down, let's look at what actually happens in each of these conditions, right? So if m is greater than n, as discussed, we have a surplus of ones compared to n's. So we'll be printing 1 1 0. If m is equal to n, we have the same number, so we'll be printing 1 together, as in with pairs. So it'll be 1 0, so that the condition or the criteria does not break. So it'll be 1 0. If n is greater than m, that means there is a 0. So we'll go ahead and print the 0. That's extra for us. And if n is equal to 0, that means we just have an extra 1. So we'll go ahead and print this extra 1. Also, while we're doing this, we obviously need to have some sort of system that tracks how many m's and how many n's we have left, or how many zeros and how many ones we have left. So we'll write all of this in a loop, which would look like while m is greater than 0 or n is greater than 0, because either of these need to be true for this to be ongoing, right? Yeah. So while this is 0, since we're printing two ones together, we'll essentially be needing to remove two ones out of our m value. So I can confidently say m minus equal to 2, and but I want n minus minus, since I'm just removing one n. Here, since it's the same, one n and one m, I'll say m minus minus and n minus minus. Since we're removing 1 0 here, I'll just say n minus minus, and for here, I'll just say m minus minus. So while this loop is going on, we're essentially having the we have the condition, we have the update, we have the loop that is going on. So we'll essentially be doing this until both m and n are greater than are both 0. Then we'll be stopping the pattern. Right. So if I were to quickly trace an example and what it would look like, let's go with this one, 4 and 8. So I write down 4 and 8, and let's just move it over here. So let's quickly check our condition first. If m is less than n minus 1. So if m, so here this is n. So let's write that down for our convenience. This is n and this is m. So if m is less than n minus 1, 8 is not less than n minus 1. So that's true. That's false, I mean. And m is greater than 2 times n plus 1. So n plus 1 is 5. 2 times 5 is 10. So m is not greater than 10. So we have this if statement sorted. We won't get a minus 1 because this is a valid number. So let's quickly go into this section here, which is the while loop we'll have for printing the pattern itself. So while m is greater than 0 and n is greater than 0, which obviously are, we'll go ahead and check the first condition where m is greater than n. Yes, since m is greater than n, we'll go ahead and burn these extra ones that we have by printing a 110. So we can say 110 and we'll be updating this and be saying, look, since we use two ones, you'll have 3 zeros and 6 ones. Oh, look, it's still m greater than 1. You still m greater than n. You still have an extra number of zeros, extra number of ones. So we'll get the same pattern again, which is 110. So this will turn out to be 1 and 4. We look at this again. M is greater than n. We still have an extra number of ones. So 110. And this turns out to be this time 0 and 2. So let's see, we have two ones here. So we get m greater than n, which is not true. M greater than n. Uh, so obviously we'll also need to check whether you know the number of zeros is still valid. So we'll need to check and n is greater than 0 while doing this. Otherwise, we would have gone ahead and printed a 110 here again, which would have been problematic because then n would be minus 1 and that would be a very, very wrong thing to happen. We check this condition, which is not true. We come to this condition m equal to n, which is also not true. We come to the condition n is greater than m, which is not true again. We find that n is greater than 0. N is equal to 0, which means we've completely exhausted the number of ones. We only get this situation when either m or the number of ones is 2 or 1. Otherwise, we would have sorted this out over here at m is greater than n or m equal to n. So there's no way that we're getting three ones simultaneously here together. So we get this, and so since we're printing 1, we can go ahead and say if you print 1, and this will be decremented by 1. So you'll have 0 and 1 here. Again, we'll go through this loop again, and we'll come back to condition 4. We'll check n is greater equal to 0 and m is equal to here. Again, we'll need to check if m is greater than 0. So since that is true, we'll print 1. So we have another 1 here. Then we'll have 0, 0. So this loop will stop executing and this will be our final answer. So if we were to quickly check, we have 1, 2, 3, 4, 5, 6, 7, 8, 8 ones and 1, 2, 3. All right, there is some sort of mistake here. Oh, okay, so there should be 2 comma 4 here, and then 1 comma 2. So since it's 4 comma 8, should be 1 1 1 0. So it'll be 4 3 6. Yep, and then 1 1 0. So it's still, since it's 1 1 2, it'll be 1 1 0 over here. Oh, my bad. So you'll have 1 1 0 1 1 0 1 1 0 1 1 0 1 1 0 1 1 0 1 1 0 1 1 1 2 3. Have this example sorted. Let's quickly look at the code and what the code of this solution looks like. is essentially more or less same to the pseudocode. We have two integers n and m. Since it's given as 10 power 6, we can safely say it's an integer. We can safely take the data type as an integer. We take in these values and we check if m is less than n minus 1 or 2 times of n plus 1 is less than m, which is essentially these conditions. And this case that we have, if this is true, we print minus C out minus 1 and then return because we don't need to check the pattern if that is true. Then if while n is greater than 0 or m is greater than 0, we have the same thing. So we'll be printing 110 for m greater than n and n greater than 0, which is completely the same thing that I've written here. Yeah. And then if m is equal to n, we'll print 10 and get subtract or take out 1 from m and n both. Else, if n is greater than m, we'll print the 10 because this is the case where m is equal to n minus 1. Else, if n is equal to 0, that means we have an extra 1 or extra ones, essentially two ones at max. So we'll print 1 and we'll print m minus minus. And that's the end of the solution. If I were to run this, I get 110, 110, 110, 110, which is the exact same solution that I wrote down over here. So that is the end of this video. Do let me know if you have any questions or if you had some sort of different approach to this problem. This is a good 1400 rated problem. It only takes a bit of logic to get this locked down. Otherwise, it's fairly simple. With that, ending this video. Thank you for watching. Do let me know if you have any questions. Tata, bye bye, good night. See you.